Good morning, and I hope you all enjoyed yesterday's class and, of course, the class on Tuesday. I guess we're starting right on time today. Uh, this is the last session, and I put together what I think covers everything that we proposed to cover. Uh, we may end a little bit early. The intention was to be done this morning in an hour, but you know that is not likely to occur. So, but what we can do is at the end, depending on our timing, I'll open the floor up to questions. And then that should wrap it up for us. Recall that this is a recorded class, which is good. That means that other people can take it. If you think it's a benefit to other people, maybe in your organization or other organizations, you can announce that to them. Then I'll make a shameless plug for a class that's being taught in June. I'm teaching an introduction to ceramic processing. So a bunch of the stuff that we're talking about this week, there just isn't time to go into much depth. Colloidal behavior being one, we're not touching on that at all. Basically, forming processes, etc., are detailed, done in much more detail. So, without further to do, as they say, here's where we are. You should be able to see my screen now. Good. Okay, so powder characterization is a recap of yesterday. We discussed powder characterization, specifically sampling being critical because you make an assumption that your sample is representative. Measure density and surface area, and then particle size distribution we spent quite a bit of time on. As we evolve more robust ways to look at particle size distributions, I think that data becomes more useful. And I think there's a big opportunity to look at particle size distribution data differently, and we're working to do that. Ceramic forming process is a pretty high elevation view: slip casting, ram pressing, extrusion, and dry pressing. And then in the end, we conclude, or I conclude, that warping and cracking are rooted in the process, not just are not an artifact of drying or firing, but they show up there. And to that point, you get approximately, drying gives us approximately 1/3 of the shrinkage for a plastic form part like extrusion. And therefore firing gives us sintering process 2/3. So if you end up with defects in the piece that show up in drying, then it's an indication that your defects are more severe than if they show up in the sintering process. Of course, the issue with the sintering process is that if it's dried and it cracks, you can recover the material. If it's sintered, it just goes into the landfill. So anyway, that's the issue here, is that this gives us an indication of the magnitude of the problem. So today what we're going to do is we're going to look at packing, because we didn't get to that yesterday very briefly. Then I'll spend time on thermal processes, drying, calcination, pyrolysis, sintering. There's some other things too, but that's the main focus. Temperature measurement and firing, a little bit of an introduction to furnaces. And then we'll talk a little bit about statistics. And of course, in statistics, sampling matters as well, but we aren't going to deal with sampling today specifically. So let's talk about particle packing. All of the models that have been developed for particle packing are based on a mono-sized spherical particle. And that's fine, and that's a good place to start, but they don't actually apply ideally to the packing of real particles, because none of those particles are spherical for the most part. The other thing is that in real powders, we always have a particle size distribution, and you know that particle size distribution is typically log normal. The other thing is morphology. And I know that the instrument makers are really excited about the fact that they've, through some photographic rooted techniques, they can get a shape of the particle, a morphology. But I will freely admit that I have no idea what to do with that data. To mathematically describe a particle that has a shape like this is a little tough for me. And it'd be great if they were, say, a nice oval particle or a football or something. You could come up with something that works reasonably well. But when we get conchoidal fracture and, well, shall we say, non-cleavage plane associated fracture in ceramic particles, the irregular shape is a problem, right? So giving me that shape piece of information doesn't help me to understand what's going on in the material. And I haven't been satisfied with the answers that I get back from the raw material suppliers or the instrument makers, excuse me. So how do you get around that? The way you get around that is you have to measure your own packing. So Pauline's rules up here on the right, Pauline's rules were developed basically, Linus Pauling, and he developed these rules to explain the packing of atoms or ions in a crystal lattice. But they apply to particle packing, particularly for spherical models. So if I have three large spheres, as you see here, okay, and these spheres basically touch in three places, the hole that's left by those spheres is 0.155 times the diameter or the radius of the large. It doesn't make a difference, diameter or radius. And so what you get is 1 over 0.155 is approximately 6.5, which is, we approximate as 7. So we say that the large sphere should be 7 times larger than the smaller sphere. And you need to keep that number in mind because it's really important for particle packing. So what that means is that I need to have a small particle that's at least 7 times smaller than my large particle. Where this becomes important is in particle packing of blending powders of different sizes, potentially to get better packing behavior to minimize shrinkage. If I have a tetrahedrally packed system, right, so you have essentially a tetrahedron, right, and you have spheres in the corners of the tetrahedron, the space in the middle is 22.5, so roughly 4 to 1. An octahedron, okay, and I don't have to draw all these for you. Okay, an octahedron are essentially faces of a cube. Okay, so you end up with this. That hole in the middle is 41%. And then cubic is what you have on the corners of this diagram. Okay, out here. Okay, if you have the corners, it's 72%. Well, it turns out we did a lot of work on particle packing, and I thought, well, I've got this hole here. I've got this 22.5, and I've got 0.414. If I have a hexagonal close packed array, I'll get both tetrahedral and octahedral spaces, and I should be able to improve my packing by doing this. It turns out that doesn't work. So if I took two powders that were, say, one was a quarter the size of the other, so my radius ratio was 4 to 1, and I blend them together, I get no improvement of packing. And it's because I just don't get those perfect packing spaces, okay? Now, if I take a hexagonal close packed array or a face-centered cubic, they're the same thing. Maximum packing I can get here is 74%. Now, if you remember from our discussions earlier, my powders typically pack to 50%. So if we look at powder packing in general, okay, this rule of thumb is really good, 50%. And I got a former student of mine called once many years ago and said, I have sand in a warehouse. His company was buying a company that did hydrofracking in Pennsylvania. And they had 3 warehouses full of sand, and they wanted to estimate the volume of sand. He says, can you do this? And I said, I don't know, I'll come take a look at it and we'll see what happens. So how do you measure big piles of sand? And the answer is you cheat. And by cheating, I mean, I went and found a surveyor. And I said, can you give me the volume of the sand? He goes, yeah, I can do that. So he came over and he ran around the mountains and he came back and he gave the volume of the sand. Then you need to know the packing behavior. So what does the sand pack to? And Turns out it packs to 50%. You can get that value for sand with a graduated cylinder. Okay, so it's not complicated. So I got 50% calculated. They had something like 53,000 tons of sand, and they had estimated 51 and a half. So we were pretty close. But anyway, packing behavior, 50%. Okay, this guy down here, this guy McGreary, if you don't have this article, if you're a member of the American Ceramic Society, you can get it for free online through the website and through Wiley. Journal American Ceramic Society, 1961. McGreary's Mechanical Packing of Spherical Particles is simply brilliant. Okay. Now, he did perfect spheres, and they're relatively large. But he looked at the size effects, there was no distribution data, etc., morphology, except interactions. These are all ignored. In his case, there are no particle interactions. In our case, when you get to fine particles, colloidal forces can take over and the particles can agglomerate. So to look at that, everything has to be greater than 35 microns to avoid colloidal, okay, which we talked about, right? And the graduated cylinder works well. You need at least 10 to 1, okay, the diameter of the cylinder that you're measuring in versus the size of the particle that's being measured. Has to be at least 10 to 1. Vibration is looked at as a way to get packing, but vibration is interesting because there's a frequency contribution that's not defined. We've done a little bit of vibration work, but you have to get something that allows you to change the amplitude of that vibration. And we don't have that readily available. And so the consequence is that we don't end up with vibration data. And it does a strange thing in your graduated cylinder, is that it when you get done, you get a dome of the powder in the graduated cylinder, okay, from vibration. If you do a tap density, and the tap density is, there's a instrument makers make it. All it does is it takes this cylinder basically, right? Graduated cylinder, typical, which is the best, and it simply bangs it up and down vertically. No side-to-side movement per se. Works very well. If you do that, plot your data on a log scale and you'll find something remarkable. Values fall between 50 and 60%, but they're typically 50%. Now, this figure on the right, what is this showing you? This is showing you that you need 10 to 1 aspect ratio. So if you look here, here's 1, and there's some funny things that go on here, as this would be the size of the particle, right? This is the diameter of the container divided by the sphere diameter. So at 10 to 1, you can see from this curve, right? When you get to about here, you get roughly no contribution to the size of the vessel. And if you want to make it better, and the rule of thumb is typically 30 to 50 x times the size. So you can see what that range is here. And this value are not that far apart. So McGreary specifies that it has to be 10 to 1. That piece of information is really important to us. That says if I want to blend large and small particles, my large particle, okay, should be 10x my small particle, okay? If I do 7x, I don't get the best packing. And partly it's because the size of that particle in between the other particles is looking at more or less a little volume within that large particle network, and it needs to be at least 10 times larger than the particle. So this is our particle packing situation, is 10 to 1. So if I take 2 powders, I want those 2 powders to be at least 10 to 1. If I take 3 powders, my large particle then is 100 times my smallest particle. And then we have to deal with the distribution, right? So we took a series of powders. Oh, I will add a little insert here, okay? So, pardon me. There we go, that's better. All right. I mentioned that you need to calculate packing of how do you estimate packing? So to get packing of real particles, okay, I have to measure the endpoints. That means I have a coarse particle, for example, right? I measure then the packing of the coarse particle. Now, you might think that if I have smaller particles, they will pack better. It turns out packing is independent of size generally, with one exception, and that exception is when colloidal forces take over or when the particles get too small, now their packing is affected. But small particles do not pack better than coarse particles. So if you take your coarse particle and you measure its packing efficiency, we'll call that PE, okay, and PE coarse, and you measure your fine particle, okay, and you get a PE fine, right? If you want to have a medium particle, you can have a PE medium, okay? What you have is the pore space within the coarse particles is then filled by the medium particles, and the pore space between the coarse and medium is filled by the fine, okay? So if I just do coarse and fine, which is fine, I say the packing efficiency of the coarse particles, 1 minus that is going to be my pore volume. And if I take my packing efficiency of coarse plus then the pore volume, 1 minus packing efficiency of coarse times the packing efficiency of the fines, okay, this will give me my packing efficiency of my sample. Okay, so the simple math would be if I say I have 50% packing efficiency, so if I have 50% here, and I have 50% here, and 50% here, okay, I can say 0.50 plus 1 minus 0.5 times 0.5 equals what? This is 0.5 plus, this is going to be 0.5 times 0.5, 0.25. This equals 0.75. So if I pack 50%, if I pack coarse particles and fine particles, I get 75% packing efficiency. And what's the ratio of those two? Well, if I do the ratio, if I have the same density powder, so I can ignore the density and the volume, I'm going to get 2/3 coarse, 1/3 fine. Okay. So that means that I would have, say, 66% coarse and 34% fine. Gives me my 75% packing efficiency, because this powder is then fitting in the holes of the coarse powders. If I broaden the particle size distribution, the powders will pack better. In my sand example, sand is a scalped distribution, meaning that the supplier of the sand cuts off the tails, the coarse end and the fine end. And for fracking, they look for a narrow particle size distribution anyway. And so they're all narrowly distributed powders, so I don't get a packing benefit by having a broad distribution. So here's a more practical view of packing. One summer, I had a series of students, it's true of all summers. So we took coarse, medium, and fine powders. These were all tabular alumina powders, okay, and obtained from a commercial supplier. So we mixed coarse, mediums, and fines, and then we did a statistical experimental design, not particularly important. The dots are the things that were measured here, such as this, okay, and this is the result of what I got. So where you would normally expect that your best ratio, based on McGreary, is 70 coarse, okay, 20 medium, and 10 fine. That's what McGreary found. And this actually fits really nicely to the equations that I generated on the previous slide. All right. So that means you would expect here that somewhere up here around 70% coarse. Okay. So here's 50, right? 50% coarse. And so 70% coarse falls right about here. And then we're 10% fines. So this would be my optimum packing predicted by McGreary for spherical particles. You can see from this figure that doesn't happen. In fact, I could blend just coarse and fine powders, right, and come up with nearly the highest density that I get in the system. It's a little hard to see in this, but this was like 76.3 here. Excuse me. This is 76.3 at this point. And over here, we are roughly 75. Okay, this is approximately 75% packing efficiency. So this whole region here is 75% packing efficiency. and I go to a peak, it's only 1% difference. Whereas if I go out to this edge, my packing efficiency falls to about 65% over here, a little less than 65% here. And the same as up here, less than 65%. But look what happens with medium. This value here is 72%. So I'm a little less than 72% here. What do we learn from this? Well, these were narrow distributions. And this was a broad distribution. So I don't have the particle size distributions to show you, but the broad distribution from medium overlap the fines in the coarse to some extent. So bringing in the medium particles didn't really improve my packing very much. Okay. Now, the problem with this is if I wanted to be a certain packing efficiency, I would have to mix my system very well. So if this is my maximum packing efficiency here in the center, okay, any deviation of packing or of mixing. So if I have a little pocket of coarse particles, I move in that direction. If I have a pocket of mediums, I move in that direction. And if I have a pocket of fines, I move in that direction. But if you notice here, this whole region that I had outlined previously is relatively uniform across this whole area. This is the opportunity for a robust process. If my blend of 3 powders falls within this region somewhere, okay, so maybe I pick it at the optimum right here, then what happens is that variations in mixing end up with a very small variation in my packing efficiency, provided I can mix sufficiently well that everything falls within this oval. Okay, and if I get really poor mixing where I have a pocket of fines, then that's going to want to shrink more, and that will lead to cracking. So my mixing that's necessary in this system is only that which is required to stay in this region. Okay, so I don't have this really stringent mixing process necessary. Now, from a manufacturing point of view, you can say, well, what does that mean for manufacturing? I mean, you tell me that I've got to have perfect mixing to make that work. And actually, I'm not. I'm saying that your mixing only has to be sufficient. Okay. And so what happens here, interestingly enough, is that our manufacturing processes are frequently robust, meaning that the manufacturing processes, the ones that work in our factory, are the ones that are able to be mixed appropriately, right? Or to the right extent. So you have a factory set up, you have a process set up, you've got a mixer, for example. I'm not going to list the mixers, but the mixer that you use is fine in your process. And then you do some iterations on the body composition, and you settle on a composition that, when used through that mixer, gives you the best properties in your material. And what that is that you have actually very likely chosen, maybe without specific knowledge, you've chosen a system that works based on the mechanics of your process. And that's an important observation because I worked with the traditional ceramic manufacturers for many years. And when we started that process, I had Buffalo China and Syracuse China and Hall China and Lenox, for example. We had a whole bunch of manufacturers. But up until that point, and you'll see this throughout the literature, there's a really great article on strength of porcelains done by two guys at American Standard. And they don't share the composition because people treated their compositions as unique and special and proprietary. Now, the funny thing is you can go buy their ware and you can send off for chemical analysis. You can come back and back out what the composition is really likely. However, right, the observation was eventually made that if you took Buffalo China's body and you put it in Syracuse China's process, it wouldn't work because all the machines at Buffalo China were set up based on the behavior of that body and the mixing of that body. And all the process equipment at Syracuse China was set up based on the properties of their body. To introduce a new body introduces a body that has different rheological behavior from what they're used to. And the companies used to buy and sell equipment. Sometimes they would buy equipment from each other. And the first thing they do is reset all the conditions and then adjust the machine until it works the way they want. So what I'm telling you is that these processes tend to be really robust. And that is great for us within manufacturing ceramics because the ability to put parts in a box is going to be dictated by the robustness of that process. And if you're out here and you've got a little window here and you're trying to operate your process in that window, or even if you're down here and you're trying to operate that process in this little window, any deviation will make a significant deviation in the packing and therefore the potential for cracking or warping. And by the way, the closer these lines appear to each other, if they're equally spaced, and they're not in this case, then the more rapid that change in density will be. Okay. Now, McGreary did us really great amount of work, right? And do highly recommend this, even if you're not in the particle packing regime. Go read what he's done. So this is your percent of theoretical density. So this is the packing efficiency essentially over here. Okay, so 75% packing efficiency sits here, for example. Okay, what he did is he looked at the diameter of large particles to small particles, or large spheres to the small spheres, and recognized that his are all very narrowly distributed. And what you look at this curve, okay, and you look at the slope of this curve, right, and the change, and you come down here to 10, right, and you say, well, at 10 versus 100 out here, or 75, right, my difference is about 1.5%. So he said, but notice that here's my 7-to-1. This is trigonopacking. This is 7-to-1 here, okay, roughly 6.5-to-1, 7-to-1. And that's actually, roughly a 2 to 3% change. So he says your minimum is 10-to-1. Okay, that's the minimum necessary for efficient packing of powders. And then this is his plot. This is coarse down here at the bottom, and this is going to fines on that side and going to mediums over here. And I show you this because here's his optimum. It's almost perfectly where I say it would be. It's pretty close. 10% fines, in this case about 22% coarse, and 68% or 22% medium, 68% coarse. But notice that if I move in this direction, the space in these lines is broad. If I move in this direction, the spacing in these lines is narrow. So as I deviate in this direction, I'm going to get a greater change in density from this optimum. Now, we did a bunch of experimental designs on packing, and I had a student working on cements, and he said, well, cement's not a ceramic material, and I would be happy to argue with you about that. But you have three components: gravel, sand, and cement is the fine powder. So based on McGreary, right, we would have predicted that this triangle up here would be our optimum packing in the system. So this is coarse on the top, that's the gravel. This is medium over here is the sand, and this is fine over here, which is the cement. We predicted here. When he did these measurements, he found that in his statistical experimental design, which is just this little triangle here, it indicated that his density was increasing like this in this direction. So he wasn't in the optimum. He wasn't even close to the optimum. So then he did a larger triangle, this larger triangle, and then he did a series of smaller triangles, and you can pick them out of here if you wish, for example, like this, okay? And he found his optimum to now be down here in this region, okay? But when we look at his, and the reason is that we look at his particle size distributions, right? This is the cement. This is the sand. And this is the gravel. Well, what you see with the gravel is very narrow distribution, okay? So it's a very narrow distribution. The mean falls right here, basically, and it goes to so it's a coarse particle. You look at the gravel, they all look the same size. We're deceived by the sand. We look at the sand, we go, oh, that looks the same size too. The tail of the sand, though, here, this is coarse down here to fine down here. So this is large particles on the left, okay, to small particles on the right. This violates our 10-to-1. And this is fine for 10-to-1. But these two, the gravel and the sand, behave the same. They basically blending sand and gravel together, which is along this axis here, okay? There's very little change in density as I blend sand and gravel, a little bit, but my cement comes in, and this whole region here turns out to be, if I had pick my optimum density, constant cement level, I can change the ratio of sand to gravel with no change in packing efficiency. And that says that my particle size distributions are not broad enough. Why am I telling you this? If you have a 200 mesh powder, right, and you decide to substitute in a 325 mesh powder for that 200 mesh powder in a packed system, what's the result? And the result in terms of packing is 0. There's no result in packing. This is 75 microns, right? This is 45 microns. This change in size is not enough to make a difference in your packing behavior. So substituting a finer material, there may be other benefits of doing that. The traditional ceramic manufacturers and porcelains took out their 200 mesh quartz and put in 325 mesh quartz, and were then surprised to find no change in shrinkage in their wear coming out of firing. So if you wanted to change this, you have to change this to a 7 micron quartz, which would be very difficult to process to change the packing behavior of the body. So small changes, what seem to be large changes, like going from a 200 mesh to a 325 mesh, doesn't actually result in a change in packing. And by the way, you see it here also. This is the previous figure. You can see that in the wet state, wet then improves the packing of the cement phase, just the fines, and it compresses this region now to be in this narrower region. And so contribution of water is then a change in van der Waals attractive force of the cement to improve the packing. But essentially no change in the packing of the gravel or the sand or the binary mixture of the two, only a change in what the cement is doing in the system. So particle packing, where do you run into trouble? You run into trouble here if you ended up with a material with a really broad tail, either fine or coarse. It could affect your packing. And so that's a good reason to measure particle size distributions to see if you have some deviation. So if, for example, you end up with a material, the sand, let's say the sand goes through a crusher and it doesn't get crushed, and you end up with a distribution does something like this, right? Now you end up with a coarse tail on that sand that might affect your process. There's a benefit of measuring particle size distribution. Okay, so that brings us to thermal processes. And I'm going to do a high elevation view of drying, and then we'll go into what's calcination and pyrolysis, annealing, because we hear that term a lot, and sintering, and then we'll talk about temperature measurement. So drying. There was some really great work done on drying in the 50s and 60s and 70s, basically. And the amount of literature on drying is just staggering. And you can sort of understand why. You have a process and everything's going along fine, and then suddenly in the middle of the afternoon, parts start coming out of the dryer cracked, and the first inclination is to go and change the dryer. But the fact is that it's probably rooted in your process. It's just showing up in the drying step. But there are 3 stages of drying. And so this is a really illustrative plot. I don't know where the little dots in the background come from, but recognize that we're for moisture content in the drying process. We're moving from here in this direction. Okay. So what we have is you get shrinkage with drying. And if you correct for that, okay, as you move down this path, if you correct for the change in the surface area associated with the shrinking body. So if you have a, say, let's just say a cylinder, for example, and it starts to dry and it shrinks when it dries, your surface area is reducing. If you correct for that change in surface area, you get what's called a constant rate period, okay? And what that is this is equivalent to evaporation from a free surface. That means that if you were to take a pan of water and set it out in the room, the evaporation rate would be the same as the evaporation rate from a ceramic body. So what happens is that during that process, and we have this little cartoon on the right, you have water separating the pores, or water separating the particles is the argument. And then as it dries, it pulls in, and that as the particles pull together, they shrink. Okay, you get shrinkage from A to B, obviously. And then that also pushes the water to the surface. And as long as it pushes the water to the surface is free evaporation. Okay. And as you continue, we'll get to a point where that process stops and there's no more shrinkage. That's here. Now what happens is your drying rate decreases because your area stays the same, but the evaporation rate decreases, and you get what's called the first falling rate period. And when you get to the point where there's only water left in the meniscus between particles, so if I draw a cartoon down here like this, and I say I've got a meniscus here of part of water in between the particles, my meniscus, that's the second falling rate period. Second falling rate period. Okay. So you have the three regions. Your opportunity for damage occurs up to this point. Okay. And that says that once the system stops shrinking, your ability.
Hi, Bill,
Yes.
sorry to interrupt. It looks like we have a question in the chat. I just wanted to let you know. You can answer it when you're ready, but I just want
Okay.
to let you know.
Okay. So we have at this point, this is our end of shrinkage, EOS. And at this point, our ability to damage the body is dramatically reduced because shrinkage is the rearrangement of particles. To be honest, I don't really like this figure. You go from A to B to C to D. This implies that this particle next to this particle, that these stay in their relative relationship to each other. But I'm convinced that if you do the addition of math of all of the water regions in this diagram, I'll do them this way, water regions here, okay, as you look at all those and you add all these up, okay, in the system, it doesn't equal the shrinkage that you see in the body. And I know this is a coarse particle example of even small particles, and you do the calculations. To me, there has to be a large amount of particle rearrangement during that drying process where particles actually move. And they probably can't move much more than a diameter, but they will move in relationship to other particles to improve the packing because of capillary forces in the drying process. But the cartoon is reasonable for us, and that's okay. So this is the general mechanics of drying. There is one other thing that occurs in here, and before I do that, let me take a look in the chat. Let me figure out how to do that. The question is, does freeze drying have similar characteristics as oven or furnace drying? And the answer is no. And so let me diverge for a moment. Let me come back to freeze drying in a second. So we'll do that this way. I gave me to spell drying correctly today. Okay, so let's go back to here. I have a free surface, okay, and I have water below, right? Water plus particles. This is my packed bed, okay? And what happens in evaporation, right? Evaporation, I get a stagnant layer on the surface, okay? Okay. That stagnant layer slows down the rate at which evaporation occurs. So I'm actually getting my free surface evaporation from here, but I have to diffuse through this layer to get to that point. So to speed up drying, okay, the tendency is to use heat, and we'll talk about heat in a second. Heat is a problem for us. Okay, so what I do though is if I set this up, right, in front of a fan, is my example of a fan, poor example of a fan, and I blow air across here. If I think it's 150 feet per minute or something like that, is my velocity. I will sweep away that stagnant layer and my evaporation rate will increase. Okay, so a simple fan will increase my evaporation, increase the drying rate. Now, what's the motivation for evaporation? Is going to be a change in humidity. So if I have low humidity, I get faster evaporation. Okay. And if I increase temperature, I increase evaporation. Okay. So, but the fan helps a lot. So we talked about gypsum molds, the 96 degree C problem where water boils at 100 and we have to dry the mold. Best way to dry mold is to set it in front of a fan and it will dry efficiently and quickly and you end up with a not undamaged mold by doing so. I'm going to add another slide. Okay. And I'm going to pull this chart up here from the previous slide. This is called a psychrometric chart. Okay. And so psychrometric charts, we're not going to go into this in a lot of detail today. I'll point out a few things. This is dry temperature, dry air down here on the x-axis. Okay. This is saturation. So this is saturation. So this is called a wet bulb temperature. So it's hard to see on this chart. You can find them online. They're really easy to find online. And then these lines here, for example, these relative humidity. This is 90 here. This is 80. This is 70, 60, 50% relative humidity. So what you get is the wet bulb temperature versus the dry bulb temperature. It's this really simple little device. Okay. You have a thermometer, right? And you have two thermometers. You can, this used to be in earth science or whatever. One has a sock around it into a little vat of water. Okay. So it's capillary action is evaporating water in the sock. This is the wet side and the dry side. Okay. And here's your temperature. This is your dry bulb temperature. Okay. Here's your temperature. And in the wet bulb, it sits here because this is evaporating and you get evaporative cooling. And by looking at the ratio of these two temperatures, you can determine how much evaporation rate there is, and you can calculate the relative humidity. Okay. The other thing to note is that this scale is the absolute humidity or the moisture content in the air. So under ambient conditions, 100% relative humidity is about 2% water. Okay. What does that mean? That means that there's a lot of water in the air. So at 50% relative humidity, you are about 1% by mass water in the air. I'm not going to go into much detail other than this. There are some really nice tutorials online for psychrometric charts. Psychrometric charts were developed to explain heating and cooling loads or to calculate heating and cooling loads for cooling buildings in particular and heating. And of course, a big player there was Carrier. Okay, freeze drying. Freeze drying is, there's a couple of ways to look at it, but freezing is a potential issue because the freezing process, there's a great thing, American Ceramic Society, I'll just write it down here. It was in the cements division, and it's George Shearer. Not quite freeze drying, but he went through and talked about how ice forms in materials, for example. Okay. But what happens is that when you have ice in a system, it tends to nucleate like in a body, even if you have the body full of water, the ice will nucleate, and then that freezing front moves across the body and it ignores the microstructure, so it goes around the pores. Freeze drying is a process by which you go to a triple point, and I'm probably not going to draw this quite properly, but I think it's temperature on this axis and pressure on this axis, and you end up with a curve looks like this, as I recall. So this is vapor here, vapor. This is let's see, liquid, and this is solid. So you have your ice here, your liquid, and your water. And this point here is called a triple point. It's where liquid, solid, and vapor are in equilibrium. That means no meniscus. No meniscus. Okay, we spelled that right. Okay, and therefore also no capillary action. This point will change with dissolved salts. The other thing that happens is as you evaporate moisture from the system, so if you go here, you can cause the solid, the ice, to move to the liquid with move to the vapor phase. That's sublimation. Liquid in the system can be avoided, so you don't get any capillary action. You could arguably be along this curve here to have the same sort of thing, but this ends up being more or less the ideal place to be, is my understanding. But it's a different aspect than evaporating water from the surface because you're actually subliming the solid in the system. And I don't know if that's helpful to your answer. Let's see, does freeze drying have similar characteristics? So it is different because you avoid the capillarity in the system, so you have a less of a chance of damage, is my recollection. But there's a potential, that's what it is. There's a potential for segregation.
Hey, good morning, Mr. Cardy. I asked a question. I'd be happy to expand on it a little bit. So I'm
Sure.
working with CMCs, and what I've seen so far is I went to a microscopy course that the manufacturer of our freeze dryer held. And one of the things that they mentioned is that when we do a faster freeze, or a lower temperature, you generally get smaller ice crystals. I guess what I'm wondering is, will the effect of smaller ice crystals produce tighter packing versus if we freeze it at a higher temperature, -10 versus -65? Will that then push those crystals apart due to the expansion of the water, or spread the
I
particles apart?
understand. Here's what I would do. Are you ready?
I am.
Go skiing.
Say, oh, just kidding.
Go skiing. Go talk to the people who make snow. And
Okay.
here's why I say that. They add chemicals to the water to increase the freezing point to a higher temperature. They're nucleating ice more efficiently. I would add that to your system to control the nucleation of ice. You're relying right now on a random nucleation event. It could be a heterogeneous nucleation event where
Mm,
it's the surface that's nucleating the ice. But if you were to introduce a chemical that facilitates ice formation, you should get a more uniform nucleation of ice in the system. Now,
sure.
I said segregation here. There's a book, now we're off topic, Michael Pollan, okay, The Botany of Desire. And if you haven't read it, you need to read it. But anyway, there's your assignment for today. He talks about apple cider. It seems like it's unrelated. It's not unrelated. He talks about apple cider and then the making of what's called Applejack, right? So this will be interesting in the midst of our ceramic processing discussion, but Applejack. And what they would do to make Applejack is they would take a barrel of hard cider and they simply leave it outside. And at that time, we were in the middle of the Little Ice Age, so we get extremely cold. And if it's down to -30 or -40, what happens is the ice then starts to form, but it takes the alcohol and it concentrates it in the center of the barrel. And so what happens in when you freeze this system, if it's not done properly, you will push any dissolved salts in the system away from that freezing front. So your salts in the system here, we'll just do like this, the salt crystals are moving with this freezing front and they're nucleating, and you'll end up with all your salt probably concentrated in the middle of your piece, assuming that you're freezing from all sides. Okay. So if you're freezing from all sides, right, then what would happen is that you would segregate your material to the center, and you may, that may be what you're seeing, is that you get segregation of your material because of that freezing front. And so it's going to push any dissolved salts in the system. Interestingly enough, it probably won't push particles in the system, because the ice, when the ice forms, and that's the George Sierra thing, when the ice forms, it completely ignores the structure of the material. And so if you had an obstacle, if you have an ice front forming here, for example, okay, and you've got your crystallographic ice forming in the system, and it moves, and you get an obstacle in the middle, this keeps going, right, across that front. And when it gets to the other side, okay, it just continues, it comes back together, and these then, they form the same crystal on the other side, having completely ignored this obstacle in the middle. As this front moves, it ignores the obstacle, whatever the thing is, and it comes around and it reforms on the other side of that inclusion. So there's no evidence that there was a structure involved in the formation of ice. And so that's how ice forms. And I would have to assume that's the same thing here. Particles are unaffected, but what is dissolved in the water does not fall out until you supersaturate that system. So in the case of Applejack right here, Applejack is a situation where by freezing, this is all the water in the system, and this is the alcohol here in the center. So then, of course, the little piece of information you don't need, but they would, to access this, they would drill a hole down and siphon the Applejack out. But this is essentially a freezing process. And I would think that your problem in freeze drying is not the evaporation of water, but is the problem of freezing, and how do you control the freezing process? Is that helpful?
Yes, absolutely. And remind me again, the Michael Pollan book that you were talking about?
Botany of Desire.
Botany of Desire. Thank you.
There'll be a quiz on this later. Okay, Botany of Desire. Yeah, great book. All right.
Thank you.
You're welcome. So there's a lot of literature on drying, and I make another distinction here. There is a great model on drying, George Shearer again, okay. There's a micromechanical model based on what happens on the particle level. Then there's a macro mechanical model of drying, which is this psychometric chart. And what I find interesting is that these two do not interact. So if the micromechanical model was sufficiently robust, and it's not an indictment of Shearer's model, but if it was sufficiently robust, you should be able to predict the conditions of drying that would give you the fastest drying rate without causing damage to the system. But there's too many variables: particle size distribution, particle packing uniformity, dissolved salts in the system, presence of organics, etc. What's the strength of the network, etc., etc., etc. Those are all problems here. And the macro mechanical model is, how fast can I evaporate water from the surface of my system? And if I can evaporate water sufficiently fast, then I can speed up my drying process. But if I evaporate too fast, okay, and the system is able to say, like here, if I have, say, a material and I evaporate too fast, I'll case harden. So I'll get a dense dry layer on the outside, right? and then I get a jelly center. Okay. And then, you know, this situation here where I have water left inside, it's like our spray dry granule, right? That forms, you know, this. I'll have to collapse that, or I'll have to do something else, but I'll end up with the problem with the low density center because I essentially caused case hardening by fast evaporation. And usually this is under the presence of high temp and low humidity. Okay. And the faster I dry it, the greater the potential to form this hard surface, or case harden, as they say. So that's where the system falls apart. Calcination. This is just for clarification of terms. Calcination is commonly thrown around as a term, and technically, or strictly speaking, calcination has to do with the treatment of limestone to form lime. You're calcining, you can see the root of the word, right? You calcine the system, you drive off the CO2 to form CaO. And as shown here, you get this porous calcium oxide layer. General picture of that. Why is it porous? Because the density of CaO is greater than the density of CaCO3, limestone. So what happens is that this means that the volume, this is in a decrease in volume associated with that reaction. So this is a nice system because you put a calcium carbonate particle in there, it loses the CO2 from the surface somewhere around 900 degrees C, okay? And then the calcium oxide layer that forms is a higher density, so it naturally cracks, and that facilitates the further elimination of CO2 from the center of that granule. So these systems, you'll see them all over Limekiln Road and that kind of thing. And they were typically on a hillside. They would feed fuel in the bottom, okay? And they would feed limestone in the top. And what comes out is burnt lime, CaO. If it's exposed long to air, forms quicklime, CaCO2, OH2, calcium hydroxide. But all through the Northeast, all through the country, frankly, you'll see limekiln roads because this was then a building material for cements. So calcination, though, has now come to mean any process that heats up material to drive off volatiles. And those can be things like here, like hydroxide, so you get H2O off. Here you get CO2 off, right? It could be in an inert environment in certain cases, but typically calcination is now a term that's used much more globally. But strictly speaking, it applies to the burning of lime to make cement, essentially. Not Portland cement, but that lime is then mixed with sand to make cement in old buildings. Pyrolysis. We see a lot more interest in pyrolysis lately, move towards organic materials, phenolic resins, and pitch and things like that. There's two routes. If the system is allowed access to oxygen, you get an exothermic reaction. That means that the system heats up. This is burning. Okay, this could be quite energetic, right? So you can set these things on fire, basically. If you starve the system for oxygen, it's an endothermic reaction, meaning that it sucks up heat. Okay, and then what's happening here is you're basically hydrocarbon cracking. We are of an opinion, I'm of an opinion, that a little bit of oxygen actually helps that process really well at lower temperatures. Okay, these are typically for organic materials, carbon-based, etc. And then there's it's a heat problem. You bring in heat, system decomposes. And then this is endothermic versus exothermic. Endothermic in our case for pyrolysis is oxygen starved, but endothermic reaction might be the melting of ice, for example. An exothermic reaction, conversely, is the formation of ice. So when ice forms, when the structure of the material becomes more ordered and more and less random. So when you go from water, which is a random structure, to ice, which is a highly ordered structure, that highly ordered structure is at a lower energy state. So that process of freezing or crystallization gives off heat. So those are exothermic. Crystallization reactions are exothermic, solidification reactions are exothermic, melting reactions, decomposition reactions typically are endothermic. So there's a lot here, but this is just for your information. And then annealing. Annealing is a process that's typically applied to metals. Okay, we really we're all, you can go to, used to be able to go to the hardware store, probably still can, and you could get a annealed copper tubing to hook up your sink, for example, and it was really easy to bend. Well, it was really easy to bend because it had been annealed. So they made the tube, and then the process of making the tube, it elongates the grains. It also piles up dislocations in the system, and it becomes embrittled and very stiff. So they would anneal it, they heat it up, and it recrystallizes all that, heals all those dislocations. Now the system is pliable again. Ceramics typically do not benefit from annealing, okay, with the exception of glass. So in glass, we anneal because if I take a sheet of glass and I cool it, okay, so my glass is hot and I cool it, okay, what I get is I get a surface, okay, the surface is then under compression. This is when cooled at room temperature. So this surface is under compression. And this surface in the center is under tension. So what we do is, the problem is then that the glass has got residual stress in it. So then you heat it up, and then these stresses will relieve. Why does it form these stress distribution? It's because the outside cools faster, and it starts to contract associated with that cooling process due to thermal expansion, and then it locks up, and the inside is still warm, still hot, still pliable, and when it tries to contract, it's constrained from contraction by what has happened on the outside. So that's where annealing comes in for glass. A similar sort of thing, you heat the material back up and you relieve the stresses. That's what's happening with metals. But in ceramics, like polycrystalline alumina, zirconia, or composites, they don't exhibit that behavior. So this is our 10 o'clock break. Let's be back at, because the next thing we're going to do is sintering, and that's going to take us a few minutes to go through sintering. So I don't want to start sintering and make it 20 after. So let's say we're back here about 10 minutes after 10. Does that work for everybody? Good. See you at 10:10. Howdy. Guess we're all set. Any questions? All right. So now we're going to talk about sintering. And sintering, this is a sort of a cartoon illustration of that. This is a fine ceramic powder, it's alumina, and then these two images are at the same magnification. And when I sinter, you see I get a polycrystalline microstructure. And you can see also that the size of the particles is dramatically smaller than the size of the grains that get formed in the system. You can see some examples where grains are close in size to the particles, but also there are larger grains. This is the nature of sintering. And they would sometimes call this exaggerated grain growth, or they would say discontinuous grain growth or whatever. But I think it's more likely that we get a log normal grain size distribution in the process. So it's not really a surprise. It's a process that almost always involves heat, particularly for ceramics. Some materials can be sintered at room temperature, calcium carbonate, for example, in the presence of a little bit of water. That's a different case. Okay. Sintering can be very sensitive to the kiln atmosphere. So if I have a system that doesn't like oxygen, like some of my carbides and nitrides, presence of oxygen can kill the sintering system. If I have a little bit of oxygen on the surface of silicon carbide during the forming process, I won't be able to sinter that material. I have to take it off in the furnace. Um, it is possible also to get coarsening where the particles get larger without densifying, and that does happen. That's called coarsening. The other thing is, and we don't touch on it much here, but this process is driven by surface area. Okay, so surface area driven. If you don't have sufficient surface area, it won't sinter. Okay, so this is a high surface area material. This material here is probably about 9 meters squared per gram. Okay, and if I were to take a coarser powder that's say 1 meter squared per gram, it simply doesn't sinter. Okay, so just keep that in mind. This is highly surface area dependent, and most of this literature was generated by the metallurgy industry in the development of sintering of powder metals and then applied to ceramics at a later date. This is an example. This is a dry part here. Okay. This is a pressed part, and this is the dense sintered part. And you can see the shrinkage. It's about 22%. Our shrinkage values for sintered ceramics range from 14% up to about 22%, maybe a little bit higher, but not by much. So that's the case. All right. So, okay. Pardon me. Okay, so I have another note down here. It says size bar. What we do typically in these systems is that we want to give an idea of what the size is in our image. Okay, and it's common to say, oh, the magnification is 1000x. That piece of information is actually useless. And the reason is that if I take an image that's this big at 1000x, and then I show the image this big, well, now it just became 4000x or something like that. And so if I put a size bar in both of these, that size bar is always correct. So I do the human hair thing as a context for you to understand things better in terms of size, and it's really useful to do it that way. But this size bar down here says 1 micron. That 1 micron size bar, if I take this, and I can do it as an illustration here, and then I'll undo it. Okay, if I take this image and I expand it, notice that the size bar expands with my expansion of the image. It's still 1 micron, no matter what expansion I do. So that size bar, that is the way to show these materials and to illustrate that information. The same is true down here for a larger specimen, right? That ruler in the image helps me to see what's going on. So it's a really good way to go about it, is to put something in the field of view. If you recall, I put a penny in the surface of the testing screens, okay? And that gave you a context for size. The same is true here. So if you're creating a report for somebody, for example, and you are and you have images, the best way to do that is to put something in the field of view that indicates size. In the microscope, electron microscope, optical microscope, that's built in, but it's best to pull it out, insert it where you want, okay? And that way, everybody can understand what the magnification is in the context of a size bar. So sintering densification, there are 3 general mechanisms for sintering: solid state, liquid phase sintering, and viscous phase sintering. This last one is for porcelains, basically, and for glass ceramics. Solid state sintering is for metals. And it turns out for almost all ceramic materials, we are in this middle range of liquid phase sintering. Okay. Now, I like the literature for sintering and densification. There are 3 stages for sintering: initial, intermediate, and final. They dug really deep on those clarifications. So in the initial stage of sintering, you get neck growth, and I'll show you an example of that in a moment. You lose most of your surface area in the initial stages of sintering. There's almost no densification occurring in that system, and coarsening actually typically doesn't occur very much unless you are held at elevated temperature for a period of time where you are growing those particles. So where does this loss in surface area come from? Loss of surface area comes from the neck formation in the system. Okay. There can be coarsening in the system in the initial stage of sintering, but a lot of that is due to neck growth. Intermediate stage sintering, the pores become distinct now. They become channels or tunnels rather than a random porosity in a network. And at the end of that process, you've eliminated the open porosity, so your surface area plummets, because then it's just the exterior of the sample. Most, 95% of your densification occurs in an intermediate stage sintering regime. And what we've found in recent years is that in that range, there's very little to no grain growth, because where I have a grain, okay, I get a pore that pins that grain that prevents the grain boundaries from moving. So this pore here prevents grain growth, basically. And the final stage of densification, pores are closed to become closed pores, and you finally densify and eliminate those pores. There is negligible surface area to begin with and no loss to speak of. Densification is final, okay? And then you get extensive grain growth in the final stages of sintering. Up here, okay, the system behaves linearly with temperature and on a log time basis, meaning that on a time basis, I might do 1 hour, 3 hours, 10 hours. That's on a log time basis, okay? 3.2 being halfway between 1 and 10, okay? So, but if I went from, say, in alumina, 1500 to 1600, okay, to get the same thing in time, I'd have to maybe have to go from 1 hour at 1500 to 10 hour, or 1 hour at 1600 to 10 hours at 1500. I don't know what that value is. It depends on the system, but time scales non-linearly on a logarithmic time basis. Temperature scales linearly. That is generally true throughout everything that we've looked at for sintering. And I encourage you not to use time as a way to achieve densification, because in most systems, temperature is driving that process. All time does is time gives you extensive grain growth. So the longer you are at temperature, it almost has no effect on densification. It only grows the grains. So if you want large grains, go to high temperature and hold. You want small grains, go to high temperature and get off of it quickly. This is a cartoon diagram here, by the way. And so this is basically this was initial stage sintering. Okay, solid state sintering means we don't form a liquid between the samples. We're left on diffusion mechanisms of atoms hopping from one place to another. Temperature is below the eutectic or below the melting point of the system. But if I bring in impurities, I can facilitate melting at much lower temperature. In the ideal condition, the sintering temperature is 80% of the melting point. This is on a Kelvin scale, okay? Meaning that it's not degrees C, which is 273 Kelvin is 0 degrees C. It's on a Kelvin scale. So my melting point for the material then is based on Kelvin. These are sophisticated models. They come from powder metallurgy, and it's common to see that for powder metals. They argue for alumina, but our data suggests it's liquid phase sintered. Ferroelectrics, zirconia are all solid state sintered, no liquid phase form. This neck is what's here. This is the neck. And you can also see the neck here. Okay, and you can see where the neck is formed between two spherical particles. I'm cheating here. This is actually nickel. Okay, but such a great illustration of neck formation that I included in the image to show you what's going on. The cartoons for intermediate stage sintering are rough, so I don't use those. We go to final stage sintering. Okay, we have this sort of situation here. Curvature. All right. we are trying to minimize energy. That's the whole point of sintering, is minimizing energy. And a high surface area powder has a lot of energy. And so by reducing that surface area, I reduce the energy in the system. Okay. So when I have curvature, all right, the curvature, if I were to take this material and say, draw a line from this point to that point, this line is shorter than this curve. Okay. That means that this curve wants to move in that direction. This line wants to move in that direction. This line wants to move in that direction. So you can see the arrows in here. Look, at 6, it doesn't want to grow. It doesn't want to move because the boundary is straight. This is 6-fold coordinated. This is 10. This is 4. This is argued to be 50. Here's 3. So a pore of 3 wants to be eliminated. That's where this diagram comes from. You come over here, okay, and you say pores grow down here, pores shrink up here. And so what you get, this is a dihedral angle. That's this angle here in this system, okay? And you get what's called an equilibrium dihedral angle, which might eliminate that line because it's just poorly placed, okay? And so what I have here is, let's say my angle is 120. Or 130, I guess it is. Okay, so is that right? 80 to 140. Yep, so 110. So let's say it's 110. So if I draw a line across here at 110, this is equilibrium. That would be this equilibrium angle over here. Then it would tell me that any pore that's coordinated with 7 or less, sits out here, those pores will shrink. If I have a larger pore, like say 10, then it's in this pore growth regime like this, and that pore will want to grow. So this is a nice microstructure, this cartoon here, because you could say this is a pore here rather than a grain. So it's sort of ambiguous in terms of what's going on, but it's illustrative of what happens in the final stages of densification. And if you look at this image on the left, and you look at the image down here on the right, you can see that curvature showing up. And if I expand this, it's easier, but the easiest one is maybe this one right here. This is a curve. It shows that this wants to move in that direction. Okay. And so, here's a straight boundary, for example, right? So you can see that this cartoon microstructure on the left is represented reasonably by the microstructure on the right. Let's talk about liquid phase sintering, okay? Really common 2-component systems. You have a high melting point crystalline phase and a low melting point crystalline phase. And the high melting point phase is marginally or partially soluble in the low melting point material. It's called a solution reprecipitation mechanism. There's some cool things that happen. For example, this meniscus here causes capillary forces that pull this particle and this particle closer together. And by doing so, they increase the pressure in this little area here, and that increases the dissolution of the high temperature material in that liquid. So it's a really elegant system in the way it works. The most common that we see is cemented carbides, or your carbide machine tools, tungsten carbide, cobalt. Cobalt's a metal, has a melting point of about 1400 degrees C, okay? And the cobalt melts, and the tungsten carbide has a finite solubility in the cobalt, and that results in the sintering of these materials called cemented carbides, okay? So you would end up with a liquid phase. Here's your liquid phase in the system. And then in the end, you end up with still having a liquid phase in the system, but on cooling, that phase crystallizes. So you have a tungsten large particle matrix, if you will, with cobalt in the grain boundaries and in the pockets. Okay. A lot of work's been done on liquid phase sintering. These are a couple of examples. This is forsterite, I believe, which is a magnesium silicate. And this is MgO down here. And what you notice is that the grains are not nice, sharp boundaries, which you typically see in sintered microstructures, but they're rounded. And that's an indication of a liquid phase sintering in this case. And you see here, like in this case here, those grains are still sharp, okay, but within a liquid phase. And here is that liquid phase, okay, whereas here is the liquid phase in this case. Again, the cartoon version, you mix the powders together. The black powders are the liquid forming system, and the larger particles are the unmeltable system or the high melting point system. Solid state reaction, the system basically, you get a little bit of motion in the system, and then the liquid phase, the black particles melt, they form a liquid that then starts to do a solution reprecipitation process. So if you have a particle like this with, say, a point on it against another particle, okay, so this is my liquid is here. I'll just draw it like this. Okay. This point will dissolve because of the pressure, and this will become curved. It will flatten that point out. These particles then move closer together, and it's affecting the sintering of the system by the presence, eliminating all these little points. That's the solution part. And then when it gets away from the pressure, it reprecipitates. So the other thing that will happen in this is the particles will rearrange due to capillary forces, and then you get the solution reprecipitation process, and then final densification. Okay, so the thing is that this would apply for alumina if I have impurities. What impurities do I have? Well, I actually have a bunch of impurities potentially, right? It could be silica, it could be calcium, it could be sodium, it could be magnesium oxide, okay, etc. And they, in the presence of these materials, they'll form a low temperature liquid that facilitates the sintering in alumina. So when you look at your 96% alumina, which is common, those impurity phases that make up the 4% can contribute to the sintering by the formation of a liquid phase. We like to talk about it as if it is solid state sintering, but it typically is not, and that liquid phase is real. Okay. Viscous phase sintering. So these are porcelains, basically, by and large, almost entirely are compose this area. So porcelain is the big one. Okay. A mixture of quartz, feldspar, and clay. These are industrial porcelain compositions in the middle. This is a portion of the potassium, alumina, silica phase diagram. Okay. And here are my compositions. This is electrical insulators here. This is sanitary ware. And here is dinnerware, essentially hotel china, hard porcelain. Okay. So I get mulite in the corner. I get feldspars over here. And this is my silica. And here is clay represented as metakaolin on the diagram. Do you care? Probably not. But essentially what happens is that this formation, a liquid phase here at 990, then that liquid phase grows, and you form densification. At the end of densification, you get about 55% liquid, which then goes to a glass, cooling at density, at densification. Unlike this system, liquid phase sintering, this might be 3% liquid in the system, a small amount, okay? This diagram over here suggests a higher amount than 3, you know, but the fact is that we're talking about a very small amount of liquid in liquid phase sintering. Here, we're talking about 50% of the final microstructure is liquid. These reaction sequences are based on the phase diagram. You can predict what's going to happen. And sometimes you get crystalline materials left over that didn't react. Other times you precipitate a crystal out of the system. And what precipitates out of porcelains is mullite. And the reason it precipitates out of mullite is because you reside in the mullite phase field. If you want to talk about phase diagrams, we can do that at another time. So let's talk about heating the system. I've not seen this chart put together often. I think it's useful for you. We have essentially in air, we have 3 types of furnaces. We used to just call these Canthal furnaces, and they were iron, chrome, aluminum alloy. These are the heat elements that are typically the spiral wire elements, okay? And then the max temperature is about 1200 degrees C. I looked it up online just out of curiosity, and They argue for 1300 as the max temperature for these furnaces. You could do that a couple times. And after that, you get to replace your heating elements. This material, iron chrome alumina, forms a protective passivation oxide layer. Okay, passivation oxide layer on the element that protects it. Turns out that also happens for molybdesilicide, and we could probably argue that it happens to some extent on silicon carbide also. Okay, so I'm going to draw that as a dash line here for silicon carbide. Silicon carbide, 1500, you could probably push it to 1600 for a little bit, but not reliably. I'd say 1550 is your true max, but 1500 is good. These elements work very well at those temperatures. They work very well above about 350 degrees C. Okay. Molybdesilicide, these are the hairpin heating elements. They typically look something like this. They come down like that. And these are your molybdesilicide. And they're good to about 1700 degrees C. Some, not all, can go to 1825. So you pay a premium for that on the element. And my understanding is that they don't know exactly why some work better than others. They usually test them to find out, but I may be wrong about that. That's just my experience. And then all three of these are in air or oxidizing environment. They work very well. If you're above that 1800 degrees C or 1700 degrees C cutoff, then you get into tungsten, metal hot zones, basically. They're called metal hot zones. They're good up to 2800 degrees C. Tungsten melts somewhere around 3400 degrees C, but this has to be in an inert atmosphere, no oxygen, okay? No oxygen, okay? Because this will very rapidly form WO3, and it will erode the element severely. The other thing is that when you go up to these temperatures, I would say a practical limit is probably around 2400 degrees C, okay? And the reason is that as you go up in temperature, this will start to creep and elongate. So it works for a while, and then you have to replace those elements as they get elongated. And then our champion here is graphite. And graphite is 3000 C. It's inert in argon, typically. It can be, these can also be, by the way, vacuum. But it's hard to maintain a vacuum at really high temperature in general. But you can use graphite up to 2200 degrees C and nitrogen. If you go above that, you start forming CN cyanide. And it's not that it's poisonous gas. You know, we can say a little glibly, we don't care about that, but we really don't in this case because it's easy to oxidize that to make it not important. But it is, the problem is that it gets the carbon to form cyanide from the graphite, so you erode your heating elements. So that's the situation for resistance heating in furnaces. We have one other that I didn't include, and that's induction. And I'll just write it on here, and we're not going to go into it, but induction, you're able to go potentially even higher than that 3000 degrees C, but you have to couple to the sample. Or you have to couple to something else that heats the sample until it will couple with an IR, with radio frequency, an RF cycling that excites the molecules or in the elements within the sample to make them heat up. Okay, sort of like, and also microwave, which I'm typically ignoring. All right, let's do a temperature measurement. Thermistors are for low temperature. We're not particularly interested in those. A lot of literature available for those, and you pick them based on your application. I'm not going to talk about those. Thermocouples, though, is our most common way to measure temperature at high temperature, okay? And so I made a list of thermocouples down here, the most common ones that I run across. Type K is the big one. 1260 or below, it's a nickel aluminum material, works in air. And then we get the platinum electrodes here, okay, or platinum thermocouples here. R and S are good to 1760. B is good to 1820. So platinum 13% rhodium, platinum 10% rhodium, platinum 30% rhodium. These are also good in air or inert. Okay. They're not good in reduction. And so what that would suggest is that there's a passivation layer formed on your nickel aluminum and your platinum thermocouples that protect it from further oxidation. Then we get into type C, which is your high temperature thermocouple up to 2300 C. And that's a tungsten rhenium thermocouple. It has to be inert or vacuum. Okay. Because tungsten rapidly oxidizes at temperatures above, surprisingly low, somewhere around 500 degrees C, maybe a little bit lower, it starts to rapidly oxidize. So how do you deal with thermocouples? We'll come back to parametric cones and I'll mention just optical pyrometers here. This technology has improved dramatically in recent years. They're good from about 1600 up to 3000. Commercially, they're in that range. So what people do is they'll do thermocouples at low temperature and then switch to an optical pyrometer as you go above that 1600 degrees C. And this is typically in your tungsten or graphite heated furnaces. And they'll integrate those two signals so that the transition from the thermocouple to the optical pyrometer is smooth. They operate up to 3000 C. They may quote you a higher temperature, but not too many things can heat above 3000 C. But the optical pyrometers are used for that application. And then you have to be able to see into your furnace. And if you can't see into your furnace, you don't get an accurate measurement. All of these materials, thermocouples and optical, or both of these, are susceptible to contamination or being obscured, okay? Blockage, we'll call it, okay? So if you look through a sight window in an inert furnace, inert atmosphere furnace, and you start building up debris on the inside of the window, you can't see your sample anymore. It will appear to be that your furnace is at a lower temperature than it actually is, and that can create a problem. If you're not familiar with thermocouples, I recommend the Omega site, okay? It's just that it's readily available. There's a number of thermocouple manufacturers. Geo2 is, I think it's Geo is one. So we have Omega. This is not an endorsement. I don't get paid by these clowns. Geo, they have information like these tables. So this is how it works. Okay, there's a number of things to note. This is a type R thermocouple. That sounds great. 13% rhodium. Okay, so it's 13% rhodium balanced platinum against platinum by itself. Those two alloys then create an electromotive force. They create a potential difference. And this is a reference junction at 0 degrees C. What does that mean? It means I start somewhere. And if you look in this chart at 0, right here, hard to see probably, but this is 0. The millivolt output at 0 is 0. And so at that temperature, okay, everything is referenced to that temperature. So in modern controllers, okay, modern controllers correct automatically for that reference junction. They will have a thermistor in the controller that looks at the temperature and then makes a correction for the temperature within the controller. And what they'll do is they'll find the millivolt value for the temperature in the controller, and then they compensate for that difference. Okay, they'll subtract that voltage from the voltage they get from the thermocouple. So this is to give you an idea. If you were at 650 degrees C, your millivolt output would be 6.157 millivolts. They register that value and they use that to control the furnace. Okay, so you have tables and you can look up that millivolt output. Now, in the modern world, we don't have to do this anymore. When I was a student, you had to go to the thermocouple tables and you read the millivolt output and you calculated what your temperature was. Okay, that's not done anymore because now they have an algorithm that looks at your millivolt output, tells the controller what to do. But I do have an interesting thing to share with you. We've run into this before, type S and type R. You look at them, they look the same. Type R was 13%, okay? This is 10% rhodium. This is 13% rhodium. And so what's the difference? Oh, well, let's look at this. Let's say I'm at 1300 degrees C with a type R thermocouple, and I measure 14.629. But let's say my controller thinks that I have a type S thermocouple. So you can come down here and say, here's 14.627. That's pretty close enough. So I have a type S thermocouple, and it's thinks it's a type S thermocouple, and but it's actually a type R thermocouple. So I think it's 1420. This is 1421. Okay, let's just say 1420, where actually the furnace is at 1300. Okay, because my type R gives me that millivolt output, and it goes to the chart and says, oh, I'm at 1420. So what it does is it thinks that it's over temperature, or it controls to that millivolt output. And so you're actually going to be at a much lower temperature than you think you are, because the system is going to correct for that. So if you swap your thermocouple in your furnace and put the wrong one in, then you'll get the wrong temperature out. And you'll notice it in your wear. Pyrometric cones. Pyrometric cones were developed by Hermann Sager in 1890. And they were a remarkable development. And unfortunately, this is the degree Fahrenheit chart. Doesn't make any difference. No, it is the degree Fahrenheit. It says degree C here, but these temperatures are in Fahrenheit. So anyway, these are viscous deformation devices. And so if you go to cone 10, okay, you have a different heating rate. If you go to cone 10 and you do a different heating rate, if you go to a faster heating rate, it represents a slightly lower temperature than if you go to a higher temperature, about 100 degrees higher. So they're actually very accurate as a temperature measurement device. They are ignored, being in the modern world as being no longer necessary, but they put them in as witness samples, meaning that they'll put cones in the kiln and look at the cone deformation on the way out to demonstrate that they got the temperature. Linearly with temperature on the log of time. So if you go up and you hold for an hour, it will appear to be a higher temperature because the system deforms. So this last 100 degrees C of the firing range, you have to maintain this heating rate, whatever it's going to be. This is 1 degree C a minute. This is 2.5 degrees C per minute. And so these are the temperatures that are referenced. So if you had a large cone, for example, large cones and small cones and self-supporting cones, they have different values, but this is a self-supporting cone here, and this is a large cone here that's not self-supporting. And so these are very efficient devices, and they're very good for just determining that you got the temperature. But if someone says they have a cone 6 body, and they often write it this way, cone 6, then that means that that material is going to sinter at somewhere around 2270. But it is possible that if they go to a slower heating rate, they'll get cone 6, but they may only be at, say, 2165. So they are telling you what the temperature is, but you have to know the heating rate and the time to temperature. Cones are still being used. I think they're very valuable. Let's talk about quality control testing. What should be tested? Well, this depends on your process, and it depends on who's in charge and what you need to test. I recommend testing incoming raw materials, and by that I mean powder characterization, density, specific surface area, particle size distribution. You can do particle packing in a graduated cylinder depending on the material, etc. I'd also recommend that you collect a witness sample. Witness sample is a small amount of material that's obtained from the batch coming in, okay, from the lot, and it's labeled and stored someplace. Doesn't have to be large. You don't have to store it very long. It should be stored for a reasonable amount of time. Certainly be stored as long as that material is in process. But recognize that if you send wear out the door and it starts failing for whatever reason, or you start to see defects generating, or you have a defect problem, you may want to be able to go back months later and look at that witness sample and see if something was amiss. For product testing, I mean, obvious things, easy things are density, usually through immersion. And I call it immersion because that's the correct term. Some people call it Archimedes, and I can tolerate that, but immersion is the correct term. This is ASTM C20. And there's a problem with the ASTM C20 in that it requires a large sample. If you can modify that for small samples by improving the resolution of your balance. So if you do a 4-place analytical balance, 0.0000, you can measure a 1 gram sample. But if the ASTM C20 calls for a 150 gram sample, so they do 0.00 balance. They have a 2-place analytical rather than a 4-place. If you do a 2-place analytical with a 1 gram sample, you get the wrong results. You get very poor repeatability. Dimensions on your wear, of course, you may measure strength. Measuring strength is not trivial. It takes a lot of time. And then you need to analyze the data. What you test, you may do electrical testing, you may do optical testing, depending on what you're making. Compile that data. So what do you do with the data? Well, we like control charts, and control charts are a way to rapidly evaluate whether your material is changing coming in. You can set control limits, you can evaluate for statistical differences, but the best possible case on a control chart, outside of always behaving the way you want it to, right? This is time on the x-axis here. This is whatever your property is, right? You will have a mean value that you're shooting for, then you have an upper control limit, right? And a lower control limit, okay? And so this is your upper control limit, your lower control limit, and your mean. And then your data comes in, and your data is doing this ideally. And then you may say that your data starts doing something like that. You can predict that you're approaching your upper control limit, and then you can affect a change ideally before it goes above the upper control limit and you're out of spec. So how do you set the control limits? They're usually established by the process, by collecting data, seeing what works, set your control limits. The tighter you make your control limits, the more expensive your raw material will be. Or if you're measuring density and your density starts creeping down, then you can anticipate a problem coming up. So here's an example of a couple control charts. These are from Buffalo, China in 2000, basically. And it provided us with an unexpected benefit. So in December of here, right about here in this chart, in November, excuse me, of 1999. Okay, the raw material came in and they dumped 50,000 pounds, 53,000 pounds of nepheline syenite to the quartz silo. Both are white powders. They look the same, but they have a very different behavior in the process. And so the consequence of that was that they had already 120,000 pounds of quartz in the quartz silo. They just added a third more, or 50% more of nepheline syenite roughly. And now they're in a situation where they either hire this guy who has a big vacuum cleaner that will let them suck out, roughly 175,000 pounds of material and discard it, or they can figure out how to use it. And so with this data here, we saw that the quartz was about 1 meter squared per gram, and the nepheline syenite was about 2.5 meters squared per gram. And through a rule of mixtures, we could calculate how much nepheline syenite was in the quartz and then compensate. Ran 14 batches, eliminating all the nepheline syenite. We recovered 51,100 pounds of nepheline syenite, so we're about 3% off, and production didn't stop. So there is sort of an unexpected benefit of having a process control chart and monitoring your incoming raw materials. So if you're interested in that, I can post a paper or drop it in the box. You just got to let me know. So we're going to talk very briefly about statistics. A Gaussian distribution or a bell-shaped curve. Everyone assumes that their data is normally distributed. And what does that mean? Means you can go into Excel, you can put in your data set, and you can calculate an average or a mean value, and then you can calculate a standard deviation. The standard deviation is a standard equation. I'm not going to give it to you, but it's easy to do within Excel or other statistical programs. You get a standard deviation. It assumes that your data is normally distributed. And if the data is normally distributed, then it follows this shaped curve. This is your bell-shaped curve here, okay? And what you get is a mean, which is here, right? And if it's symmetrical about the mean, then it's a normal distribution, equal halves, it says. So if it's symmetrical about the mean, it's normally distributed. If the curve looks like this, right, and comes down like this, okay, this is then normal axis here, right? This is your frequency. So this is frequency on this side, okay? Then this is typically log normal. So if you take the log of the x-axis, this becomes your Gaussian curve, okay? Our particle size distributions are log normal. So what you have is in this curve, one standard deviation, here's -1, here's +1. This area under the curve constitutes 68.3% of all the samples. If you go 2 standard deviations out to here, right, then we're talking about 95.5% of all your data is at 2 standard deviations. Okay. And if I go all the way out to 3, I don't really gain that much. I go to 99.7. So this tells me then what the range of my data is in terms of its repeatability. So the way that we represent that on a plot is through the use of an error bar, okay? And usually the error bar, I say usually, represents 1 standard deviation or 68% of the data, okay? Because it's an error bar, I have a point, right? Then I write an error bar and I go up and minus. This is my minus standard deviation, this is my plus standard deviation, and this is my mean, okay? Now, it's unfortunate we use sigma for standard deviation, and we also use sigma for strength, but I'm just going to ask you to keep track of that for the time being. All right. Sometimes error bars are designated as 2 standard deviations. That's why I say usually, and they'll tell you error bars are 2 standard deviations. I showed you this data. We've done this a bunch. This is porcelain, okay, densification, okay, and notice the standard deviation error bars. They are present. In some cases, they're so small that they are obscured by the data point itself, okay? So the standard deviations are smaller than the data point, but, and that happens because the data is remarkably consistent. And the difference would be, in this situation, would be a narrower distribution, you know, like this, right? It could be at the same height, okay, it comes back down, it has a narrow distribution. It should be similar in shape to that, but a narrow distribution is a smaller standard deviation. So that's what the bars represent. I recommend that when you measure some things, usually 5 data points is sufficient. You may decide that you want to measure more specimens to figure out what the range of that data is in general. And then you can establish a standard deviation that applies to all your measurements. That's not unreasonable. Density measurements, shrinkage measurements tend to be remarkably consistent. Therefore, the standard deviations are small. So you might be able to measure just a few samples or 5 samples and get a reasonable number. Some things such as strengths are very broad. ASTM 1161 tells us that we have to measure 30 specimens in strength to get enough data to do a Weibull distribution. And I'm not going to go into Weibull today. So lastly, troubleshooting, okay? Identify the root cause if you can. That sounds silly, but I do a lot of consulting with industry, and a lot of the time is spent figuring out what the cause is. And the benefit of identifying the right problem is that you don't waste time chasing a problem that doesn't exist. Look at the frequency of the problem, and that's this chart on the right. And that may sound silly. I'm gonna make this a little bigger. What are we talking about? I was in a situation many years ago, called in because they had setter plates in the kiln. And their failure rates were really interesting because they were running about 8% failure. So the failure of these pieces was right around 8%, approximately 8%. Okay. And they were remarkably consistent in that 8%, and they all developed a very specific type of crack. And in the discussions, I came back and I said, how are these made? And they said, oh, they're made by slip casting. And I said, how many plates do you cast out of a given batch? And they said that they cast 12. And you go to 12 here, and what you see here is this is 8.3%, right? So the thing is that they were casting in that suspension, they were casting these plates, and as they were casting in the time required, it sounds silly that this is the case, time required, 11 were fine, the last one there had been sedimentation, and that piece always cracked. And by stopping halfway through and mixing that slurry in their slip casting, that problem went away. So what I'm suggesting is, if you look at the statistics for the failure, what the frequency is of the failure, you might be able to go back in the process and find out a process where you do X number, and by the time you get to the end, you have a problem. The next thing, collect an appropriate amount of data points, of course. Seek advice and share observations. This is my experience. People on the shop floor and the people who are doing the work often make really good observations. And those who fashion themselves engineers or have, you know, a lot of education will discount that. Don't discount that. People on the shop floor, people who are handling the material will see things that we will never see. And if you ask them, they'll often tell you, and they know what's going on, but they don't get asked, and use the statistics in order to predict what's going to happen. So that wraps it up for me, I think. Properties of ceramics in the upper right. Defects are rooted in the manufacturing process, are not eliminated by sintering, excuse me. Cracking and drying and sintering is a manifestation of our process defects. Manufacturing processes are by themselves robust. We start with powders, so characterize the powders, and statistics will help us to understand the range of variability that we see in the system. So I talked about thermal shock, but I don't think we have time unless you wish me to talk about thermal shock, in which case I can do that quickly. Questions for me?
I've got time to hear about thermal shock.
All right. Do go and fill out the course evaluations. Don't be shy. Tell me what you think.
You're not going to talk about thermal shock?
Yeah, I'm going to talk about thermal shock now. You want to talk about it? So,
Real quick.
stand by. Okay. So, thermal shock. This guy, Hasselman, used to be thermal shock was that you would have a delta T that led to failure. Okay. And Hasselman, who was a really famous theoretical mechanics guy, he said, no, it's not. It's actually the concept of damage. So what he did was they took a series of rods, okay, they have a delta T here, and they measured strength. And they looked at those rods, and then they thermal shocked them, right? And they got this, and then abruptly, at a specific temperature, this is their critical temperature, the strength dropped. For alumina, this value, delta T, is 150 degrees C. So what happens? What happens in thermal shock is you have a thermal expansion coefficient, okay, which is X times 10 to the minus 6 per degree C times a T value, delta T. And this gives you a strain value. And if that strain value exceeds the strain of failure, you get cracking. So in these thermal shock problems, they would have, say, a rectangular bar like this, okay? And they would see cracks that occur on the surface, okay? And the reason is that the surface cooled and the interior remained hot, and the cracks would propagate to the point where this had enough time to come back up to the same temperature basically. So they create enough strain. These cracks on the surface, which look like this, are all over the surface, right? Became the critical flaws. That caused this drop in the strength in the system is when you form these cracks. So the way that it works is that we have a cooling from the surface, right? But the interior remains hot. And so that puts the surface then in tension. I drew it in compression. But what happens is because it is contracting, it places the surface in tension. I got it right. The inside remains in compression, which is fine, except it's irrelevant. So when the tension here, when the strain associated with that tension, which is related to this alpha times delta T, when the strain exceeds the critical point, the system fails. So what are the contributing factors? Strength, the thermal expansion coefficient is 1. Okay. Heat transfer in the system is another, although this is a minor contribution typically in the system, but you will find it's present in things like aluminum oxide, which has low thermal conductivity versus silicon carbide, which has high thermal conductivity. So you get better thermal shock out of silicon carbide than out of alumina. And then there is, of course, a strength contribution. So if strength goes up, your thermal shock goes up. If thermal expansion coefficient goes down, your thermal shock improves. And if your thermal conductivity goes up, your thermal shock improves. Thermal shock improve. Okay, so there are some notorious examples of thermal shock. One of our worst ceramic materials for thermal shock is MgO. And if you look up the values for MgO, right, it has a CTE of about 13 times 10 to the minus 6. If you look at alumina, its CTE is about 9, silicon carbide is about 4.5. So as the thermal expansion coefficient goes down and as the strength goes up, the thermal shock improves. This is a bit of a misleading statement because we really want our strain and failure to increase, but we equate that with strength. So that pretty much sums up pretty high elevation view of thermal shock. There's a good article in the First Science of Whiteworks proceeding by Robert Moore on thermal shock behavior for porcelains, and they did a bunch of work on that. The other thing, by the way, is if you thermal shock the sample, the scattering in your data decreases because you've introduced a huge critical flaw now that controls the strength in the system. So the strength decreases, but the distribution of strengths decrease also. So you get a very narrow strength distribution. That's thermal shock. Is that good?
That was great, Bill. Thank you for, thinking on the fly with that there. So appreciate
You're
it.
welcome. Any questions for me before we sign off?
Class is great. Thank you very much.
You're welcome. So the original PowerPoints are posted on Dropbox, and then the annotated PowerPoints are on Dropbox, which correspond with the videos because it's all recorded. So you can go back and put that. Coarse naphthalene cyanide paper in the Dropbox. I will do that.
And the lecture recordings are also available through the Dropbox, so you guys can just access them through the file called lecture recordings. They'll have the link and the password on there. It'll just take you back to Zoom and you can access them through there. And those lecture recordings should be available for you guys for a whole year. If you guys have any issues accessing the Dropbox or the file or anything like that, please just email me. You guys have gotten a few emails from mpaul@ceramics, but that's me. And yeah, and you can just email me. I'll send those links directly to you. Yeah, thank you for taking the course, and please fill out the course evaluation survey. You'll get an email again later today with the course evaluation link, but that really helps us, tailor the courses for our attendees. So,
And I haven't looked at the course evaluation, but if there's something that you thought was going to be covered and wasn't covered, or something that you would like to see covered that wasn't covered, put that in the comments. If there was something that you think was just a gross waste of time, you can tell me that as well. So we're interested in the feedback. So great.
Perfect. Well,
Mhm.
thanks, Bill. I'll go ahead and
Welcome.
stop the recording now.